Welcome back. So far we have seen that basically the mechanics by which this turbulence can essentially enter inside the flame structure and distort it. So we have seen that in different regimes, that is especially demarcated by Kolovitz number. So when the Kolovitz number is small, so the essentially the laminar structure of the flame is retained. Of course it can be stretched, that is you see, and we have also discussed this concept of stretch in the sense that when you have this tangential stretch, when you have essentially flow non-uniformities along the tangential plane of a flame surface, or when you have a flame that is curved and which is moving with the flame speed. So in that cases, of course you can have flame stretch, and in those regions basically when the Kolovitz number is less than 1, we can essentially consider this flames, the local flamelet, the local flame structure, to be essentially that of a stretched laminar flame. Okay, because when the Kolovitz number is less than 1, your flame is bent. Your flame may not be straight or planar laminar as such, it can be bent, but and there can be some flow non-uniformities also. So the flame can be stretched, so which will essentially lead to increasing the flame surface area, but that does not mean that the turbulence has essentially created some structural change inside the flame. Okay, now of course that can happen. You have seen from the regime diagrams that this considering or abstracting this a turbulent flame as an ensemble of stretched laminar flamelet, as I have said, that this works in a regime where the Kolovitz number is actually less than 1 or Damköhler number greater than 1, but in a regime where the Kolovitz number is very large, this really does not work well. Okay, because it is not only the flames are stretched, of course they are stretched, that is true, but in more than the fact that they are stretched, there is some inside disturbance of created by turbulence, that is turbulent flames, turbulent eddies, or small scale turbulence, in the sense that Kolmogorov size eddies can enter inside the flame structure and create disruption. But you have to understand that the flame is just not a benign object, it is not a passive structure, it has got strong heat release. So when there is strong heat release, there is strong gas acceleration also. So it is possible that the turbulence can also be destroyed by the flame. So it is a two-way coupling process. Okay. So on one hand you can have turbulence impinging on a flame and stretching, wrinkling, folding it, and even changing its structure at multitude of length and time scales. On the other hand, you have basically can have regimes or you can have basically have situations where the turbulence can be essentially also destroyed or can be changed by the heat release rate and subsequent gas expansion by the flame. So these two are basically competing effects, and these two have been kind of in a simplified manner, very much simplified manner. We have essentially simplified them and this competing effects in this regime diagrams. Okay. Now then of course we discuss the concept of stretch, and next we go into this flamelet norm models for premixed combustion in turbulence. So now the basic assumption of the flamelet models is that basically these are typically applicable for low Kolovitz number, large Damköhler number flames, that is basically these are applicable for situations where we do not consider any disturbance or distortion of the inner flame structure or the preheat zone structure or the reaction zone structure of the flame by the impinging turbulence. So we just consider that the flame is essentially wrinkled, and it is wrinkled at a multitude of length and time scales, and that of course has still it changes the global properties of the flame, because once it is the flame is wrinkled, its surface area is much larger, and then on the surface area is larger, then it can consume more fuel air mixture per unit time, and it can statistically it can propagate at a much faster rate. So still that description is not trivial, it has to be, one has to consider that things, but here we will consider essentially this these flamelet models, because those are much simpler, and explaining going into this regimes where the turbulence distorts the flame structure, that requires much more complicated or complex analysis of turbulence flame interaction. So here we will restrict ourselves to the flamelet models. Now there are basically two types of flamelet models that we will discuss, and the inherent assumption is that the flame has infinitesimally thin, which correspond to infinitely fast chemistry limit. So it is basically infinitesimally thin rather than decimally thin, okay, and which correspond to the infinitely fast chemistry limit. So this is the assumption that the flame is very thin compared to any structure of any turbulent flame structure. So it is the characteristic length scale of the flame is smaller than any turbulent structure, and it corresponds to the infinitely fast chemistry limit, okay. And so the Flamelet models are based on the two things, that is the progress, that is a scalar variable g and the progress variable c, and basically the inherent assumption is that we do not even need this thing, that is it need not be infinitesimally correspond to fast chemistry. We just need to consider these flames that are infinitesimally thin compared to the any structure in turbulence. So and this we will consider for basically two approaches. One is for the, we will use this G-equation model and the progress variable model, okay. So we will come into this what this G-equation are, and these are the two basically models that we will consider, the scalar variable g and the progress variable c, okay. Now we will come to this, but the c is essentially a non-dimensional temperature difference, and this is T minus Tu divided by Tb minus Tu. So as you can see that the c can only attain this T, since this T can attain a minimum value of Tu, so that time c is equal to 0 when T is equal to Tu, and it can attain a maximum value of 1, that will happen when T is equal to Tb, okay. So the between c basically varies between 0 and 1, okay, and this is what we will consider. But before that we go into this G-equation, okay. Now this is a little conceptually very interesting thing. So the thing is that you have seen, once again we go back, keep going back to this thing. You see here, this is what we are showing here is essentially surface that we have taken out of the flame, okay. So the actual flame, if we is essentially thick, so if we just so the actual flame is thicker, so it can be like if you take the structure, it will be something like this, okay. There will be like a it will be a thicker object, but what we have taken is that we have just taken one surface out of it, okay, and one surface out of it, and just showing that how the turbulence interacts with the flame. So what if we consider that the flame is infinitesimally thin compared to turbulence, and that the entire reaction, okay, is happening inside this infinitesimally thin object. Of course it's a two-dimensional, it's a complex surface. So where of course the thickness of the surface is infinitesimally thin, and the reaction is concentrated in that infinitesimally thin surface, and this surface, okay, how do you determine or describe a surface? As you know, a surface can be determined by a level set value. So what that means is that if you have a surface like this, I say that this function g x y z t, this is determined by the surface that g x y z t is equal to 0 or is equal to with any constant g 0 as such. But let us say this we determine by the surface as g x y z t is equal to 0. As a very good example is that if you want to determine if you have a sphere in space, how do you describe it? You describe it by this thing, that you say that it's x square plus y square plus z square is equal to say if the radius of the circle is 5 unit square is equal to 5 square, okay. So this is my say this is equal to 25, okay. So this then this whole thing is my g, okay. So then I describe this surface of the sphere as g x y z because if it is not moving as essentially x square plus y square plus z square, okay, and I can put 25 also on this side, and this is equal to 0, okay. So this is how then the whole surface of this sphere is essentially determined by this thing g is equal to 0, okay. So this is how you essentially come to this G-equation description. This is essentially a level set description. So you consider different so you consider a function which is distributed in space, and by selecting this iso values of these functions, that is in this case the iso value of the function is 0, by selecting proper iso values of this function you determine you can describe a complex surface, you can describe a convoluted shape of the surface, alright. So this is how you can go with this G-equation description, okay. It's essentially the equation governing a is essentially an equation for governing a propagating surface in a flow, Okay. So, this is evolved from this level set description by Osher and Sethian in the late 90s and early 2000s, and then this combustion community adopted this. So, we said that suppose you have suppose you if you go back to the previous description of the laminar flame structure. So, in the infinitesimally thin reaction limit, it is this is the structure. So, this is Tu, this is Tb. If we go to 2 dimension, it will be a surface like this. Okay. And now, if you have turbulence, this surface can be like this. That's what we just saw, right. This one can be a complicated surface, and we determine this surface as G x. This is a position vector x t is equal to 0. Okay. So, this is the description. Okay. Of course, this is can also be described as G x t equal to 0. So, initially my surface was whatever that is that this surface, whether it is planar or convoluted, this is described by my function, which is G x t is equal to G x t is equal to 0. All right. So, now we can we say that this when this G is this is the flame surface. Okay, the flame surface, which is essentially a reacting propagating surface. Of course, in this G equation description we do not consider any reaction as such, but it is a propagating surface. Okay, we say that this surface is described by this level set value of 0. So, this way we say that this surface is essentially is given by G equal to 0, G x t equal to 0. And this here my G value is less than 0, and in the product side, which is downstream of the surface, my G value is greater than 0. So, this is the description. So, if this is my flow inside a channel, and this is my flame which is given by G x t is equal to 0. So, there also can be G values here, there also can be level set values here. So, these are given by all G x t less than 0, and these are given by G x t greater than 0. So, this is the G x t G equation description, and of course, at this point the surface moves, and the surface moves of course with a local flame speed, which is equal to the velocity of the surface relative to the local fluid velocity. Okay. So, this is the flame speed with which it is moved, and it is in the normal direction, of course. Okay. So, this surface is propagating with the local flame speed in the direction normal to itself. So, this is the thing, and then we can of course this thing that it we see that it propagates a local displacement flame speed along normal vector. And how can you find the normal vector? The normal vector is find out like minus G divided by mod of grad G. It can be true, it is true for any scalar function for which you are seeking the normal. Okay, is the definition. So, this is the description that you have an this is the flames. If this is my this is my configuration, you have this is my G x t is equal to 0. Okay, this is my flame, and this is my here my G x t is equal to 0, and on the left hand side we have unbound gas, you have G is equal to negative. That is the level set value of G is equal to negative. Okay, in this one, and on the right hand side we have bound gas where the G is essentially positive, and here it is basically propagating due to two effects. The surface is moving and convoluting or stretching, whatever you call, whatever is happening is due to two effects. Number one, there can be it is stretching or wrinkling due to the flow non-uniformities, which is created by if there is non-uniform flow upstream, that is if there is a turbulent flow upstream which is non-uniform instantaneously and in point wise. So, this u x t. So, it is moving due to two effects. Number one in u x t, and which is imposed by turbulence, and it is moving due to its own propagation due to s d and x t. So, these two effects must be inbuilt into the G equation model. All right. So, then we need to find out essentially what is the G equation model. So, what we can do is that just like we can do the Taylor series expansion. So, we can write this thing that is G at x plus delta x and at t plus time delta t. We expand around the G value at x and t, okay, and that is given by, since G is a function of both x and t, it is given by partial d partial dg partial dt or dou g dou t times dt plus delta x times gradient of g plus higher order terms which we neglect. Okay. So, this is a first order Taylor series expansion. Okay. Now, so this is we can write of course for any function, and g is of course a function. Okay. Now, since what you have to remember is that the value of g at x plus delta x and t plus delta t, if it is of the same surface, okay, then the value of g does not change. So, to give you an example, this is my chamber. So, this is my say g x t and this is equal to 0. Now, when this surface will move, okay, or I will use the same color actually. We will say after some time or in a very short after some small delta t or some big delta t, it moves g x plus delta x times t plus delta t. Okay. It has moved this much. The value it will take, because it is a level set function, is still equal to 0. Another good example is to describe you is this thing, that suppose you had a sphere. Okay, it is a spherical flame which is given by g, as you remember, x t is equal to 0, and this g is essentially, here we know the function, in this case we may not know the exact functional form because it is not a regular surface. Okay, this is equal to 0. Now, after some time, say this surface, this flame expanded and it become like this. Okay. So, this is g x bar t x and this value is still equal to 0 because it is the same level set surface. Okay. So, the value that is taken by g, the value that is taken by g, this function, that does not change, which is equal to 0 or which is equal to g 0. Okay. In this particular case it is equal to 0, which is essentially a constant. Okay. If you are denoted by g 0, it is you can it is an arbitrary value, or if you denote it by 0, it is 0. And if you take the limit, say delta t tends to 0, let us put it 0 itself instead of g 0, that is creating a confusion. Okay. So, if you now take a limit in this thing, so these two terms basically cancel out because these are both equal to 0. So, we are left with essentially dou g. So, in this thing we are left with essentially dou g dou t times delta t plus delta x times grad g is equal to 0. This is, if we take delta t downstairs, what is this delta x delta t? This is nothing but the rate of propagation of the surface itself. Okay. And now, if we take limit delta t tends to 0, okay, which is equal to Vf, that is the velocity of the flame. This is not the flame speed, okay. This is the velocity of the flame surface, or the velocity of this surface g. Okay. And now, if we decompose this, this dx dt is nothing but it contains contribution from two things. Why does the flame move? The flame moves because there is a fluid velocity, or because of the local flame speed. So, u plus s d, okay, and n is equal to minus n vector is equal to minus grad g divided by mod of grad g. So, then if we just plug this thing here, what we get is this thing, the g equation, dou g dou t plus u vector grad g is equal to s d times mod of grad g. Okay. The mod of grad g comes from this normal actually. So, this is the G equation, alright. Now, using this, what is the advantage? Using this you can describe basically this is essentially a field equation. Okay. Using this you can describe the motion of a complicated flame surface or the evolution of a propagating surface under the influence of a non-uniform flow field. Okay. That is the thing, you can describe any complicated surface with this. So, this G equation is essentially a Hamilton-Jacobi equation similar to the and is essentially one outcome of the level set methods. Okay. So, this is the G equation modeling that we have taken up. Okay. So, now this thing we can we can use essentially to describe the motion of a convoluted surface, and this is typically, once again if we go back here, that this sort of motion which you see that is essentially once again I keep coming back this because it's a beautiful video which captures essentially the how turbulence interacts with the flame. So, you can capture this kind of a surface formation and deformation that happens due to this due to presence of turbulence and using the G equation, though this is not a G equation as such. This video is obtained by doing direct numerical simulation with all detailed chemistry and everything, but you can capture this sort of motion of a flame using the G equation. So, that is the very powerful nature of G equation, and next we will take up the progress variable modeling. So, you see we have just obtained this G equation, and one most important term in this G equation is the right hand side, okay, which is actually a nonlinear term, that is SD times mod of grad G. But here you need basically you see this is you have this presence of this local displacement flame speed. Okay. It is the local speed with which the flame propagates with respect to the local flow velocity in the direction of the local surface normal. But now the thing is that what is the value of this SD? Okay, what is the flame displacement speed? Now, if it was a planar laminar premixed flame, okay, then this SD would have been the exact value of the planar laminar flame speed that we had obtained. Okay. So, if you remember that we obtained this value F0 square is equal to lambda by Cp times Bc. I mean, I will not go into that. It was F0 square is equal to lambda by Cp times Bc times e to the power minus of Arrhenius number divided by Lewis number times Lewis number divided by Zeldovich number squared. Okay. Divided by Zeldovich number. So, this was that was our expression for the planar laminar flame speed, and we have obtained expressions for we have obtained experimentally or using computations we can obtain these values for different for more complex situations where you consider detailed chemistry. Okay. So, that is this is one can obtain a value of SL0, but this SD, this displacement flame speed of a convoluted flame structure like this, okay, in a turbulent flow field which is of interest, is not equal to SL0, because of course you can see that the flame is not planar, and B, the fact is that this there can be a curvature. For example, you see here there is a curvature, and of course because you have there can be flow non-uniformities also. So, when you have these two things, then what you have seen already that there is a flame stretch. And what this flame stretch does, okay, what this flame stretch does, especially when the Lewis number is non-unity, is that it causes a differential diffusion of thermal flux, of heat flux, and the scalar diffusion. Okay. And so the scalar flux, the species flux, which carries essentially the enthalpy of formation, okay, as well as the thermal flux. So, these are not matched. Okay. As a result of that, the local temperature changes, and when the local temperature changes, the local flame speed also changes. So, as a result of this, when a flame is stretched and the Lewis number is not equal to 1, then depending on the sign of stretch, whether it is positive or negative, and depending on whether the Lewis number is greater than 1 or less than 1, the local flame speeds can change. So, this is a very important thing. So, when the local flame speeds change, of course, you see that your displacement flame speed is not equal to the planar laminar flame speed, and you need to basically have models or basically have to have some database by which you can have this local displacement flame speed. So, of course, you see that in the G equation that there are two things, of course, that you have the there are a few things actually. You have the transient term, you have the convection term, and you have this propagation term. Okay. So, this is the transient term, this is the convection term, and this is the propagation term. So, there are two units which are required. So, one unit is of course one input, two inputs that are required. So, one input is of course you have to specify the local fluid velocity. Okay. So, this can be obtained by solving either the continuity and the momentum equation simultaneously, or if you have a solved u field you can put that, but of course then you cannot have a thing that when the where you should your u should change. So, it is better to basically solve this u and this coupled with the momentum equation, and then you can essentially then you can have an equation, then you need an input for the displacement flame speed also. So, these two inputs are required. Okay. So, this can be obtained from the Navier-Stokes equation, and this can be modeled. Okay. So, this SD can be essentially modeled. Alright. So, how do you model it? So, you can basically model it by using this linear stretch model. There can be numerous complicated models also, but basically it assumes that the local flame structure is that of same as that of a laminar flame. So, you can say that this local flame speed SD is essentially is equal to SL, which is the planar laminar flame speed minus a constant called a proportionality constant called a Markstein length times curvature. Okay, times stretch rate, sorry. So, this is stretch rate, and essentially this is a Markstein length usually which is obtained from experiments or simulations, and this curvature, this stretch rate, sorry, this kappa, this stretch rate is essentially contains this tangential strain rate which arises from the non-uniformity of the flow velocities along the tangential plane of the flame surface, and times the planar laminar flame speed SL. Here this is essentially a model, and times the curvature. This is the K is the K is essentially the curvature. Okay. So, this is one model that you can use. So, once you plug this in, what you get is essentially that USL minus this thing. Once you plug this in, you essentially get SD is equal to SL minus SL well minus LMK minus LMT, which can be essentially we can write it as SL times 1 minus LM kappa by the curvature minus LM times AT. Okay. There are different forms available. Actually, this is a little more complex. It is actually one can find as f square log f square is equal to minus 2 sigma, where that is a stretch, but let us not go into that in this simplified model. Okay. So, the above expression is actually valid for weak stretch limits, because the model assumes a linear response of flame to stretch, and we have to note that the stretch rate expression, we note that the stretch rate expression, that is this kappa in SL, is used to keep things easy for modeling, and it is only an approximation. Okay. So, this is the thing, and so you see that we have obtained the G equation, and which needs basically two things. One is the flow velocity and one is the local flame speed, local displacement flame speed. The flow velocity can be obtained from the Navier-Stokes equation, and whereas this SD equation can be modeled, and there are different techniques to solve the G equation, but there are actually very specialized techniques to solve the G equation, but the one has to be very careful with the solution. There are many intricate things, and you can refer any level set book if you want to solve this, but this gives you a very nice idea of how to basically have an idea of the overall flame structure, overall complex flame structure in turbulent flows. In the next step, we will take up this progress variable approach, where we will look into the Bray-Moss-Levy model. So, till then, thank you.